So in the matter of time, we move on to the next presentation, which is given in person by Ulrich Meyer on the cos-G gravity field models.
Do you hear me this time? Great, yes. I will present gravity field models of the combination surface for time variable gravity fields. Why? Well, you all know we need these models for orbit determination, and during the 4 or 5 years I've been working with SLR, I was confronted with 3 different versions of this a priori gravity field model, always provided in a different file format. And whenever I was adapting our reading routine, I was wondering, why don't we use the products, or at least the standard formats of the dedicated IAG service? Maybe it's just not well known, so let me do some advertisement here. I will first introduce the combination service for time variable gravity fields. Well, you all know about the IAG with all the different technique-specific services. The ILS is one of them. There are others, and there is this International Gravity Field Service with several sub-services dedicated to individual products. And there is this product center of the gravity field service, cos-G, product center for time variable gravity fields. If you want to have more information, you will find it on the webpage of the IAG, or specifically on the IGFS webpage. There you have this cos-G. A little bit about the history of this combination service. It started monthly solutions at that time of the GRACE mission, monthly gravity field solutions, and we think that they have the same signal content, but they differ in noise. So we do a combination. The expectation is that the noise level will somehow drop in the combination, and so the signal-to-noise ratio of the combined product will be better. Meanwhile, the service was taken over by the AAG. Now it's a cos-G combination service. I will not go into details on the product, on the workflow, but just a few words. We do a harmonization of the gravity fields before combination. We do a quality control. Then we do a combination. We have 2 schemes, either on solution level or on normal equation level. We derive weights with variance component estimation. And finally, we have a validation, internal and external, of the combined products. So we provide quality-controlled combined gravity fields. Our products are monthly gravity fields, first of the GRACE, now of the GRACE follow-on mission. They are provided in an operational scheme, and the latency is 2 to 3 months. That depends on the availability of the monthly solutions from the different analysis centers. Of course, this is not yet reasonable for operational use. I will come back to this later. Here you see the weights that we apply by this variance component estimation. In the top plot and in the bottom plot, you see an independent noise assessment by the variations of the ocean. And you see the weights, they correspond more or less to the noise assessment. And in black, you have the noise assessment for the combined solution. And for almost all of the monthly solutions, it's as good or even better than the best individual solution. So that meets our expectation of an improved combined product. Where do you get these products? Well, there's a dedicated service of the International Center for Global Earth Models. There you can get all these monthly gravity fields and all the static ones. And there's a dedicated section for cos-G models with, you have the GRACE follow-on, and even swarm monthly gravity field models. And then you have a special product that's a fitted model, seasonal trends and seasonal signals fitted to the monthly solutions of GRACE follow-on. So this model will enable prediction of gravity variations, and this model is suited for operational use. And the format is also standard for a long time now. You have, it's called this GFC format. You have the gravity field coefficients, and we have the trend and cosine and sine terms of these periodic variations. And this is extension, it's version 2. You can also apply a time window, so we can fit this model to different time spans all in one file, and then you have to check when from which time window you really need the coefficients. A few more words on this model. So we still believe the best information is in the monthly gravity fields of Grace, the Grace follow-on. And so we compare the fitted signal model to these monthly models. So here I have plotted the differences over the continents, time series. And there are standard models like this Eigen GHS Release 4 that were used for a long time. So it's not our invention, this fitting of a model. But this Eigen model was fitted on the Grace period, where the fit is very nice, and no data of Grace follow-on is included, so there it trends away. Then I made one fit of the whole time series Grace and Grace follow-on with one parameter set, and one dedicated to Grace follow-on, only with one parameter set for Grace follow-on, and we believe this model is the best to predict for use in operational LEO-POD. I will skip a few slides because I got new results that I added at the end, but at least here's something on the, we have made some orbit validation with the Sentinel orbits. They are at an orbit altitude from about 800 kilometers. These are carrier phase RMS shown, and we have in green, we have the monthly models, it's barely visible. In blue, we have the fit from the Eigen model that's outdated for Grace follow-on. And then we have different model versions of this fitted COSG model. They just differ by the amount of data that was included. And 2020 was always fully covered by data. There you see that the fitted models are as good as the monthly models. And then here you see they differ, and the more data is included, the better the fit is. So our conclusion is we have to update this fitted signal model, and it's updated every 3 months to always provide the best possible predictions. We also have independent SLR validation for this Sentinel orbits. And you see from the Eigen model to the monthly models, we have a quality gain of about 10% in the RMS orbit fit. And if you use this fitted model, it's almost as good as the monthly ones. So we don't see any reason why not to use this fitted model. We don't lose significant amount of data of time variable gravity. And now this is not an outlook anymore, it becomes reality already. The Copernicus community asked us, couldn't we provide a fit for the whole period? Because they not only want to use it for Grace, for LEO-POD, but also for reprocessing campaigns. So I fitted a model to Grace and Grace follow-on, and for the Grace period, I fitted it in yearly batches with continuity conditions. So here you see the fit for 3 river basins with annual variations and some interannual changes. And the black dots are the monthly solutions, and the red one is the fitted model. Very nice fit. Then we have the gap between Grace and Grace follow-on. And for Grace follow-on, I just used one parameter set to fit the model. The fit is not so nice, but the goal there is different. We want to provide stable predictions. And to provide stable predictions, we need more than 1 year of data. And now I will apply this model for SLR orbit determination. And why do I have to do? We see it's a good model. Well, there is one problem. It's based on Grace data. And we all know that Grace is not good in C20, but SLR depends on C20. And so here I plotted a time series. That's a priori model used some time ago by the ILRS with the weekly solutions for C20 in black. And then what you get if you have the annual variations from the Grace model. And you see the phase is nice, but the annual amplitude is much smaller. And if you include also semi-annual variations, yeah, it doesn't really change the picture. So can we use this model for SLR? Well, yes, we can. We made, my co-author Linda made experiments with 3 different sets of parameterization because we have a dedicated parameter in our SLR orbit determination. It's the periodic cross-track variation, an empirical parameter, to absorb any mismodeling in C20. And so we made first a number of tests excluding this parameter to see the full impact of this bad C20 on the orbits. Then some tests including this parameter, and then the last test estimating C20 directly instead of relying on this cross-check parameter. And we always made tests with either a static field, GTM05, or the time variations provided by LRS, or this cost G-fitted signal model. And we looked at the Earth orientation parameters, X and Y pole, because we have the experience that they are most sensitive to any model changes that we apply. And you can see that if you do not apply any absorption parameters, still the Cauchy FSM, the fitted signal model, performs best. So red indicates best. So obviously, the improvement in other parameters outweighs the problems in C20. If we co-estimate cross-track, then the RMS gets smaller, but still we see the best values for this Cauchy fitted signal model. And if we co-estimate C20, then we are more or less independent of the a priori, and here we ran out of time, but compared to the static one, we still see, even then we see an improvement, because there are other gravity field coefficients that are not co-estimated. And I'm coming to the end. For these three cases, I also have the time series available. So 2015 was our year that we processed. And here we have the three lines. Blue is for the static model, and red and green for the time variable a priori models. And you see that somehow the peaks here, the outliers are reduced when you start with a time variable model, here without having this cross-track parameter. If you co-estimate the cross-track parameter, the scatter is much reduced, and the lines are much closer to each other, but we still see there is a benefit from this Cauchy model. And if we co-estimate C20, then, well, we do not expect too many changes. We absorb everything by the estimated parameter. And then, yeah, you can start with whatever you want. That's my last slide. I don't want to draw any conclusions. You can draw conclusions by yourself. But I guess I will base our future SLR processing on the Cauchy models, because there I can guarantee the format will stay the same as long as I do the models. Thank you.
Thank you, Uli. Are there questions on-site or online? No? So maybe I can ask a question. So you did your tests using the Lagier satellite, which is not so sensitive for the higher degree in order terms. What about doing the test for LARES? Or?
We will continue testing. It's just that we had very little time because I'm running around advertising our models all over the world. So I just implemented this mid of last week, and Linda had some night shifts to do the tests for LAGES. We will repeat for LARES, and yeah, I will let you know if you encounter any problems that may avoid us from using this model. But I don't really expect problems.
Very good. Thank you very much.